Here I will explain concept related to precision rectification. Semiconductor diodes need a minimum forward bias for conduction to start. The minimum voltage called threshold or cut-in voltage is 0.3 volts for germanium and 0.7 volts for silicon. Because of this behavior, diodes cannot be used to rectify AC voltages in the millivolts range. Millivolts range. This is the diode characteristics up to 0.7 volts for silicon diode, 0.7 for silicon diode. The diode does not conduct. The diode does not conduct. 0.3 volts for germanium. 0.3 volts for germanium. This is the cut-in voltage or threshold voltage. The minimum voltage called threshold or cut-in voltage is 0.3 volts for germanium and 0.7 volts for silicon. Because of this behavior, diodes cannot be used to rectify AC voltages in millivolts range. Millivolts range means 0 volts to 7 volts. In that region, the diode is off. In that region, the diode is off. Therefore, it cannot rectify this voltages. This voltage is generally millivolts range. Millivolts. Millivoltage range. Millivolts range. From 0 to 0.7 volts, the diode is not conducting. That is the range is from 0 to 0.7 volt is the millivolts range. The threshold voltage can be effectively reduced. See the instead of 0.7 volts, the diode is conducting from 0 volts. From 0 volts like that. The threshold voltage can be effectively reduced from 0 points to 0.7 to some 0 or some millivolts range. Millivolts. The threshold voltage can be effectively reduced by using the diode in the feedback loop of the op amp. Feedback loop of the op amp, thereby enabling the diode to rectify small voltages. The resulting circuits are called precision rectifiers. Precision means exactly. Without any delay, the diode is conducting. In this case, in the conventional rectifiers, to 0.7 volts, the diode does not conduct. After that only the diode is in conducting mode. Rectification will start after 0.7 volts. Some delay is there. Here, some rectification in that case, because of this behavior, diodes cannot be used to rectify AC voltages in the millivolt range. Coming to this one, the threshold voltage can be effectively reduced by using the diodes in the feedback loop of the op amp. Later I will discuss. Thereby enabling the diodes to rectify small voltages. Small voltages means millivolts range. The resulting circuits are called precision rectifiers. These are called as precision rectifiers. Precision rectifiers. Recall from basic circuit principles that rectifier circuits can be implemented with a diode. That means half wave rectifier, diodes, full wave rectifier. Generally, rectifiers can be implemented by using diodes. Half wave rectifier we use one diode, full wave rectifiers we use more than two diodes. The major limitations of these circuits is that they cannot rectify voltage below 0.7 volts. This is the VI. This one is VI. VI to 0.7 volts. The diode does not conduct to 0.7 volts. The major limitations of the circuit is that they cannot rectify voltages below VDR. That means this is 0.7 volts, the cut-in voltage of the diode. In the circuit, Vi has to rise to threshold of the order of VDR. That means 0.7 volts for silicon, 0.3 volts for germanium. In these circuits, Vi has to rise to a threshold voltage, threshold of order of VDR. That means Vi greater than or equal to 0.7 volts. Before any appreciable change can be seen at the output. Then only have to see some appreciable change at the output. Therefore, above this threshold, we have V naught is equal to Vi minus VDR. That means Vi minus 0.7. And below threshold, that means less than 0.7 volts, V naught is equal to 0 volt. V naught is equal to 0 volts. This is the input voltage. This one is Vi, 0.7 volts. Below this 0.7 volts, output is 0, V naught is 0. Above this 7 volts, VA is allowed like that. Like that. Some distortion is result here. This is the distortion. In this circuit, VA has to rise to a threshold of the order of VDR before any appreciable change can be seen at the output. V0 is equal to output voltage of the rectifier is equal to Vi minus VDR. For Vi greater than VDR, V naught is equal to 0 volts. For Vi less than VDR. Vi less than VDR, V naught is equal to 0. Vi is greater than VDR. V naught is equal to Vi minus VDR. Vi minus VDR. Due to this output of the conventional rectifier is distorted as shown in figure. This is the distortion. Below this 0.7 volts, rectification has not done. Above this 0.7 volts, rectification has done in conventional rectifiers. To achieve precision rectification, we need to circuit that keeps V naught equal to Vi for Vi is greater than 0. Instead of Vi greater than 0.7, we need to decrease this threshold voltage to 0, Vi greater than 0. That is called as exact rectification. That is called as precision. To achieve precision rectification, we need a circuit that keeps V naught is equal to Vi for Vi is greater than 0. This is very, very important. Without any distortion, whatever the input is there, that input appears at the output. Instead of 0.7 volts, the diode conducts Vi is greater than 0. Positive going cycle. This can be in order to reduce that threshold voltage from 0.7 volts to 0 volts. We use precision rectification. To achieve precision rectification, we need a circuit that keeps V naught equal to Vi for Vi greater than 0. This can be achieved by using op-amp along with the diodes, and these circuits are called precision rectifiers. These are used to precisely rectify voltages having amplitude less than 0.7 volts. Hence, these circuits are called small signal precision rectifiers. In conventional voltage rectifiers, rectification has been done when Vi is greater than 0.7 volts. In case of precision case, Vi, the threshold voltage is reduced from 0.7 volts to 0 volts. That means less than. These are used to precisely rectify voltage having amplitude less than 0.7 volts. Hence, these circuits are called small signal precision rectifiers. Precision rectifiers are two types: half wave rectifier and full wave rectifier. Precision half wave rectifiers and precision full wave rectifiers. This one is precision half wave rectifier. Precision half wave rectifiers are two types: positive half wave rectifier and negative half wave rectifier. This one is V naught dash. This is the VD. The voltage across diode is VD. This one is V0. This one is VAOL. First, positive precision of a rectifier. This is the positive precision of a rectifier. We know that V0 dash is equal to this one is VID. V0 dash is equal to AOL into VID. AOL VID is equal to VP minus VN. VP minus VN. AOL VP is VN. VP is VN minus VN is here VN is V0. VN is V0. Vn is V0. Here apply, this is the equation 1. Apply KVL here plus minus KVL to this loop plus V0 dash minus VD minus V0 is equal to 0. This one is second equation. Second equation. Substitute first equation and second equation. Here V0 dash is equal to, instead of V0 dash is equal to AOL into Vin minus V0 minus VD minus V0 is equal to 0. AOL Vin minus AOL V0 minus VD minus V0 is equal to 0. AOL Vin minus VD is equal to V0 into 1 plus AOL. Therefore, V0 is equal to AOL Vin minus VD by 1 plus AOL. 1 plus AOL. Therefore, V0 is equal to 1 plus AOL is approximately equal to AOL. 1 plus AOL is approximately equal to AOL. AOL Vin by AOL minus VD by AOL. VD by AOL. Here AOL is cancelled. Therefore, V0 is equal to Vin minus AD by AOL. AD by, this one not AD, VD by AOL. VD by AOL. VD is equal to cut-in voltage of the diode 0.7. AOL is equal to generally 10 power 5. Therefore, VD by AOL is equal to 0.7 by 10 power 5. 0.7 by 10 power 5. This one is change this one into my microvolts. 0.7 by 10 power 5. Numerator and denominator is multiplied with 10. 7 microvolts. 7 microvolts. This is the VD dash. Generally, VD dash is equal to VD by AOL. VD by AOL. In conventional rectifiers, this one is VD. Here, VD. In case of op amp, VD dash is equal to VD by AOL. This is approximately 7 microvolts means approximately equal to 0 volts. Therefore, V0 is equal to Vin. V0 is equal to Vin. Now we have to check the when V0 is equal to Vn. Two cases are there. Case 1, Vi is greater than Vd dash or Vd by AOL. And case 2, VA is less than VD dash. That means VD by AOL. Check these two, need to verify these two conditions. If VD by AOL is approximately equal to 0 volts, is approximately equal to 0 volts. VA is greater than 0. VA is greater than 0. That means VA is greater than 0. The V naught is equal to VA. Check these conditions. When V naught equal to VA, when VA is greater than 0 and VA is less than 0. This one is VA is 0, greater than 0, VA less than 0. The cut-in voltage is changed from the cut-in voltage of the conventional rectifier is VD, changed to uh, VD by AOL. For changing this cut-in voltage from VD to VD by AOL, we use some op-amp and diodes. The diode is put in closed loop. The diode D is in closed loop. Then only VD changes to VD by AOL. VD is 0.7 volts for silicon. Here 7 microvolts. 7 microvolts. Here up to 0.7 volts, the diode D does not conduct. Here in this, even 0 volt small voltages, the diode D is conduct. The diode D is conduct. Therefore, rectification is has been done from millivolts range also. In this case, the rectification has been done from 0.7 volts. The drawbacks of the conventional op rectifier is eliminated by using this op-amp rectifiers. The diode D is in closed loop. The diode D is in closed loop. Next, to check the condition, VA is case 1. VA is greater than 0. VA is greater than 0 means here V naught dash is equal to AOL into V naught dash is more positive, because VA is greater than 0 means that is connected to positive. Therefore, V naught dash is positive, or else V naught dash is equal to AOL into Vn. AOL into Vn minus V naught. This is positive. This one is positive. AOL into positive is positive. The diode D is in forward bias condition. It acts as closed switch. Acts as closed switch. Therefore, this circuit is changed to case 1, VA is greater than 0. V naught dash is equal to AOL into Vin minus V naught. Vin minus V naught. VA is greater than 0 means this one is positive. V naught dash is also positive. The diode here AOL VID positive. This one is connected to diode D here. Diode D. This one is V naught dash. This one is V naught dash is equal to AOL and VID positive. The diode is in conducting mode, acts as closed switch. Acts as closed. Now the diode is replaced. The circuit is replaced with minus plus here. This one is VA. Acts as a closed switch. The load resistance RL is connected here. Is V naught. This one is that. This one is Vn, V positive. Vn, V positive. Vn is equal to V naught. Vn is equal to V naught. These two virtually shorted. V naught to Vp. Vp is equal to Va. Vp is equal to Va. Va is greater than 0. Va is greater than 0 means positive going pulse. Va is greater than 0 means positive going pulse. At that instant, output voltage is equal to input voltage. Output voltage is equal to input voltage when Va is greater than 0. This is the voltage follower circuit. This is the voltage follower circuit. Voltage follower circuit. Whatever the voltage here appear at the input side, Va greater than 0, the output is also like that. The output is same as input when Vi is greater than 0. In case 2, Vi less than 0. Vi is less than 0. Here, here negative into positive, negative, here negative. The diode D is in reverse bias condition. The diode D is in reverse condition. Reverse bias condition. The diode D is in reverse bias condition. Therefore, does not conduct. It acts as a open switch. It acts as open switch. Open switch means here minus plus. The load resistance is like that. Here V0. This one is Vn, Vp, Vi less than 0. Vi is less than 0. That means under reverse bias condition here, negative peak, negative half of the sine waveform. It is open circuited condition. V0 is equal to 0. V0 is equal to, there is no 0 because there is no current flow through this RL. Some discontinuity is there. For input Vi is a negative half cycle. Therefore, output V0 is 0. Output V0 is 0. Combined effect, consider this combined effect here. Input voltage Vi. This one is time period T. The diode D is on. The diode D is on. Positive cycle. Whatever that positive cycle appear at the input. This one is Vi is greater than 0. Appears here. V0 is equal to Vi. Of cycle of that input waveform. Diode D off. There is no current flow through this load resistance. Output is 0. Output is 0. Like that, in that fashion. Only this is the positive of precision of a rectifier. Positive precision of a rectifier. Only positive pulses are allowed. Positive pulses are allowed. These are the positive pulses. Next one is the negative precision. Negative precision of a rectifier. Negative precision of a rectifier. In that case, the diode D is reversed here. Minus plus. This one is Vi. The diode is reverse action compared to positive precision of a rectifier. This one is RL. This one is V0. Like that. This one is diode T. When Vi is greater than 0, here positive, here the positive is there. That positive nature of this one, diode is in open circuited condition. Open circuited condition. RL is equal, V0 is equal to 0. V0 is equal to 0. When Vi less than 0, negative half cycle of that input waveform. Here this one is negative. The diode is forward biased. The diode is forward biased, acts as a closed switch. In that case, V0 is equal to Vn. This one is Vp is equal to Vi. V0 is equal to Vn. Vp is equal to Va. Therefore, output voltage is equal to input voltage. This is a voltage follower. This one is the voltage follower. Output voltage is equal to input voltage when Vi less than 0. When Vi less than 0. This is the input waveform. This one is input waveform. Output wave positive half cycle of the input waveform 0. Negative half cycle of the input waveform in 0. V not equal to that fashion. These are the two